Hello, welcome back to Math 332 Linear Algebra. In this video, we are going to look at another very important concept for this course. That's the concept of linear combinations and another related concept called span. So think of it this way. Suppose you have vectors v1, v2, and v3. So what we want to do is that we want to multiply vectors v1 with a scalar k1, multiply vectors v2 with another scalar k2, and sum it up. So you're looking at k1 v1 plus k2 v2, and you want to see whether or not it is equals to v3. So if it is equal to v3, then we say that the vector v3 can be written as a linear combinations of vectors v1 and v2. So what happens is you basically adjusting, okay? You rescale your vectors v1 by either expanding it or contracting it, depending on what kind of case that you multiply it with, so that you can, by adjusting, rescaling, so that you can see whether or not the sum can equals to v3. So you are looking at whether v3 can be reached by this vector v1 and v2. So it's the concept of linear combination and span will be related to the concept of reachability. Can you reach the vector v3 by modifying your vectors v1 and v2? So again, you can see in this video that this concept not only apply to the usual vectors that we know that is in R2 or R3, it actually applies to all the vectors that we are familiar with. So you can do the same process for vectors that is in P2. So those are polynomial. Or you can also do it for vectors that is in M 2 by 2. There's a sets of all the 2 by 2 matrices and so on and so forth. So this is the first time you kind of like apply a concept that is originally kind of like designed for vectors that is in R2 and R3, but it's actually, you can apply exactly the same process to look at the other vectors that we learned from the previous module. Okay, so let's get right to it. All right, let's begin by looking at the objective for this video. So at the end of this video, you should be able to know what does it mean to say that this vectors is a linear combination of these vectors. And also, if you are given a particular vectors, you should be able to determine whether this vector is an element of the set, okay? All right, so let's start by looking at a very simple example. So you can verify very easily that these vectors, we are in R3, okay? So this vectors 1, 1, negative 6, can be written like this. So it is 2 times of this vectors minus 1 times of this vectors. Okay, so if you can do it like that, if you can express a vectors in this form, then we will say that this vectors is a linear combinations of the following 2 vectors right here. So what happened is that you have vector 1, 1, 6, and you can kind of like readjust, like you have to rescale these vectors. You rescale these vectors so that the sum will equal to that. Rescaling means here, example, like for example, right here, you can see that you need to multiply these vectors by 2. So you are extending the length of these vectors by 2. And then you have to change the direction of these vectors. So this vectors is pointing like this originally, but you have to multiply negative to it. So you are reversing these directions, but not changing its length. You're just reversing its directions so that the sum of this will equal to this. So you are modifying these 2 vectors by rescaling it, and then you add these 2 vectors together using vectors additions. And if you can do all this operation and get these vectors, then we will say that this vectors 1, 1, negative 6 is reachable. The concept of reachability is reachable by these 2 vectors. Because we are in a vector space, so in a vector space, the only type of operations that we can do is scalar multiplication in additions. So that basically means that if you are in a vector space, and these are the only 2 operations that is allowed, can you use those operations? Can you use this scalar multiplications and vector additions so that this, okay, adjusting and fine-tuning these 2 vectors will be able to get you 1, 1, negative 6, okay? So if you can do that, then the vectors 1, 1, negative 6 is reachable. You can reach them, basically, so to speak. You can reach the vector 1, 1, negative 6 by just playing with these 2 vectors, okay? So this is the idea behind the terminology called linear combinations. So let's look at the definitions to make it more precise. So you have a vectors W in the vector space V. So W is said to be a linear combination of all these vectors if you can express W in this form. So you can see this, what happened here is basically you are rescaling. your vector v1, we are rescaling the vector v2, you are rescaling all the vectors here. Rescaling, not only you are changing the length, you can also change the directions because your k could be negative, right? So if you can adjusting all these vectors v1 all the way to vr so that you can sum up to w, then w is reachable. It's reachable from this v1 all the way to vr. So you can get w by adjusting all your vectors here. So this this k1, k2 are the scalar, also known as the coefficients. Okay, so that's the geometrical interpretation behind that. All right, if you don't like geometry, you don't have to worry about it. You just have to keep following these definitions. And I'm going to show you a few examples. Computationally, this is something that's very easy to do, okay? So this is one of the example. The question is, if you are given this vector 1, 2, 3, can you write as a linear combination of these two vectors? Which means that can you find these two numbers, x and y, so that x multiply this and y multiply this, and then you sum it up? Can you get 1, 2, 3? So can you play with these two vectors by readjusting the length and the directions so that the sum, the vector sum, will give you these vectors 1, 2, 3. So this is again the concept of reachability. Can you reach the vector 1, 2, 3 by playing and modifying these two vectors that you have right here? Okay, and so I hope you will be able to see that finding x and y, finding these two number x and y, is equivalent to this augmented matrix. So what happened is that you will see that, hopefully you will see pretty easily by now, that this is the same as solving the system of linear equations. So you can put it into a matrix form. Okay, you can put it in the matrix form, which has this augmented form. And if you RREF to this matrix, so you row reduce to this RREF matrix, you can immediately see that our x is 3 and our y is 2. So which means that we actually know 3 of this and 2 of this will get you this. And you can verify that pretty easily. So because 3 of these vectors and 2 of these vectors give you this, so by definition, we will say that this vector 1, 2, and 3 is a linear combination of the following two vectors. Okay, all right, so we basically do nothing but using the definitions. So we are still in R3. This is another example. Question is this vectors is a linear combination of these two? Well, set up these equations. So alpha of this, beta of this, set it equals to 2, 3, and 4, and this is again equivalent to this augmented matrix. Row reduces it, you get this, which means, what do you see? You see that this linear system is actually inconsistent. There's no solutions because of this. All right, this means 0 alpha plus 0 beta equals to -2. You can see there's no way to find these two numbers so that this equality will hold. So that is an inconsistent system. That means that these vectors 2, 3, and 4 is out of reach. You cannot get them. You cannot get these vectors 2, 3, and 4 by just playing with these two vectors. It's not reachable. Okay, it is not reachable. So you can't get that. Okay, so this is what we say that these vectors 2, 3, and 4 is not cannot be written as a linear combination of the following two vectors. So the concept of reachability is not too hard to grasp, especially when you are in R3, R2, you can imagine them. So for example, let me give you x, y, and z. All right, so let me give you two vectors that is on the xy plane. So let's say that this vector is v1, this vector is v2. All right, so this vector v1 is, let's say 1, 0, let's say 1, 1, 0, and this vector is v2 here, let's say is 2, 3, 0. And you have a vectors that is right here, right? Let's say this vectors is 0, 0, 5. And you can see that no matter how you linearly combine these two vectors, you always get into the xy plane. You can't get to this, right? No matter how you do the linear combinations, you just can't get to this vector. So this vectors is out of reach. So these vectors cannot be written as a linear combination of this. This is a very easy example that you don't even have to do any computation. You can see that no matter how you adjust it, the third component is always 0. There's no way you can get 5. So this is a very easy example that you can see vector 0, 0, 5 is not reachable. You can't get them. by playing around with this vectors 1, 1, 0 and this vectors 2, 3, 0. Okay, but the other example is harder to see it that way. So you really can't really like, this is like not obvious, it's not trivial. So you really have to put them into a linear system and row reduce. So the methods of row reduction is the method of solving system of linear equation is critical actually throughout this course. Okay, all right. So what is the concept of span then? So the span, okay, is closely related with the concept of linear combination. So let's look at them, the definitions. Okay, so if you have a set of vectors v1 all the way to vk, all right, let's say they are in Rn first. This Rn can be replaced by any vector space. So the linear combinations of all these vectors is, if you put them together, if you look at a set of all these linear combinations of v1 all the way to vk, then we call them the span of this vector. So the span of this vectors is the set. Okay, so obviously it's the sets of all the possible linear combination of these vectors. Okay, so this is a set. So let me write it down. So so the span, all right. So the span, let's say v1, v2. The span of v1, v2 is a set. Okay, it's a set of all the possible linear combinations. So this is set builder notations, right? It's a set builder notations. So I'm expressing my elements. So either you do it like this or you do a vertical line. Let's do a vertical line here. So you're looking at all the element that looks like this, where your k1, k2 can change. So you're looking at 3 v1s, 2 v2, 0 v1, 1 v2, negative 4 v1, 5 v2, all the possible linear combinations, all right? So there are infinitely many elements inside here. So the set, which consists of all the linear combination of these two vectors, is known as the span of v1 and v2. All right, so the span of v1 and v2. So this definition here, we are writing everything in Rn, but this Rn can be replaced by any vectors, any vector space V. Okay, so we'll look at all this example later for the general vector spaces. But right now, let's just concentrate on Rn so that things is easier to comprehend. Okay. All right. So let's look at this following example here. So they want you to show that the span of these two vectors is R2. Okay. So if you see that if you have a span of these vectors equals to Rn, then this is known as a spanning set for Rn. So basically, they want you to show that. So you look at the definition here. So you basically want you to show that the sets right here consists of these two vectors. It's a spanning set for R2. All right. Geometrically, it means that you want to show that every vectors that is in R2 can be reached by these two vectors right here by adjusting the length and so on and so forth. Okay. So let's see. How do we show that? So recall that this is a set, right? This is also a set. So when you have two sets, okay, sets A and sets B, how do you show that these two sets are equal? Well, you show that these two sets are equal to each other by first showing that A is a subset of B, which means that you want to show that everything in A is in B, all right? And then you will have to show that everything in B is also in A. So you want to show that B is subset of A. So if you can show that A is subset of B and B is subset of A, then these two sets will be the same, right? So these two sets will be the same. So you're showing two sets are the same. You have to show that one set is subset of another, and then reverse the order and show it that it also holds the other way around. All right. So my question is that how do you show that A is subset of B? Well, you just have to take an element in A and show that if you are in A, you will be in B. And same thing here. If you want to show that B is a subset of A, you take an element that is in B and show that it has to be in A. Okay. Okay. Right. So right now we would want to show that these two sets are the same. So this is a set. Okay. This is a set, right? So I can write this thing down. This here, the span here, this is all the possible linear combinations. This is k1 of 1, negative 1, plus k2 of 1, 2. Okay, so k1, k2 are any real numbers, all right? So this is the set right here. And R2 is obviously the set of all the, and let's call it x and y, right? Where x, y here are real numbers. So you want to show that these two sets are the same, right? Which means every element that is in here, every element in here is in here. So one of the obvious thing is that you can see that this inclusions is easier, right? This inclusion is very obvious. All right, you see that? So you see that this inclusion is obvious because everything inside this span is vectors that looks like this. Obviously, this is a vectors that is like this, right? So everything that is in the span is in R2. This is obvious because all this element here is in R2. All right, this is the obvious directions. The other not so obvious direction is this part right here. Okay, so how do you know every vectors in R2 can be written as a linear combination of these two vectors? This is not obvious. Do you see that one of the direction is pretty straightforward? Okay, this one is pretty straightforward. Take an element that is in the span. It's obviously in the form of something and then something. So this is an element. Whatever element that is in this span, this sets right here, they are in the form of this, right? So this is definitely in R2. That's obvious. But right now, you're taking an element that is in R2, let's say 7, 8. Okay? How do you know 7, 8 can be written as a linear combination of these two? All right, but you can show it for 7, 8 because there are infinitely many elements in R2. If you show 7, 8, you have to show 1, 0, and then you have to show 5, 7. You have to show -4, 5. You have to show -3. I mean, there are infinitely many elements here, so you can't show it one by one. So this is going to be, you have to find a way to avoid showing it one by one. So you have to show it in general. So this abstractions is coming in. So things is going to get a little bit abstract because you can't show it one by one. So one way to deal with it, is to pick an element. Don't specify what that element is. Just pick an element and say, this is AB. I don't know what A is. I don't know what B is, but they are fixed. This is a fixed element, okay? So this is a fixed element, okay? This is a fixed real number. This is a fixed real number. I don't know what that number is, but they are not changing, okay? So this is what we call a fixed arbitrary vectors, okay? So you pick an element in R2, say AB. So these are not changing. These are not a variable, okay? These are some numbers. We don't specify the number yet, but these are not variable. They are not changing, okay? So the question is, if you are given these vectors AB, can you find these two numbers, K1 and K2, such that K1 of this vectors and K2 of this vector will equals to AB? So this is basically checking whether or not this arbitrary fixed vector can be written as a linear combinations of these following two vectors. All right, so if you want to show that element that is in here, this is what you need to do. You want to show that you will be able to find the K1 and K2 such that K1 of these vectors and K2 of these vectors will equals to this vectors AB. All right, recall that the sets here is like this, right? So you want to pick an element AB, and you want to show it that you can write it like this. You can write it like this. This vectors is qualified as an element of that set. Okay, so how do we do that? Well, there are several ways you can do that. One thing you can do is to, again, write this in the augmented matrix like this. And this time, unfortunately, you can't really use your calculator to do row reductions. You will really have to do it by hand. But it's not too difficult to do it by hand because the number here is pretty easy. So if you do it by hand, you can see that this system has an augmented matrix that looks like this and can be row reduced into this RREF matrix. So immediately you will see that this system is consistent. We have solutions. And in fact, this is giving you the answer for K1, and this is giving you the answer of K2. So this is K1, this is K2. K1 and K2 is your unknown here. K1 and K2 is your unknown here, right? So your K1 and K2 is the unknown. A, B are not the variable, okay? Your variable here are the K1, K2. All right, so obviously, if you want to solve these questions, you will expect your K1 and K2 to be in AB, right? It has to relate it to AB. If I ask you to solve for this system and your K1 is number is 2, K3, K2 is the number 5, there's just no way to get AB, right? So it's completely reasonable that your K1 and K2 here is related to AB. All right, so now we have this. So what does it mean? What does this thing means? It means that no matter what's your AB that is in R2, I can always find my K1 and K2. I can always know how to adjust these vectors and adjust this vector so to get AB. And in fact, I know the precise methods to adjust the K1 and K2. And this is how you adjust your K1 and K2. I know a way to change my K1 and K2 depending on what AB that you give me. So if you give me any type of AB, I know how to deal with this. I know exactly what my K1 and K2 is, so that I have this equality. All right, which means, what does it mean? It means that every vector that is in R2 can be written as a linear combination of these two vectors. In fact, if I can show you even how to do it, this is how I do it. All right, so that means that we do have this inclusion. We do have this inclusion. Everything in here is in here. All right, so these two sets is actually the same. So these two sets is actually the same. So we have the conclusions that the span of these two vectors is actually R2. Everything that is in R2 is reachable by these two vectors. Okay, and there's another way to show this. Okay, this is not the only way. You can show that the span of these two vectors is R2. This is another way. Okay, so slightly easier way, but it didn't provide that much information, but it will still works. That is, okay, so this is again similar. So now take a fixed elements A, B, and try to show for this. So remember, this system is the same as this, okay? So you look at this matrix here. This matrix here is invertible. So I know my K1 and K2 is basically 1, 1, negative 1, 2 inverse times AB. So I don't have to compute this. You can compute this, but I don't even have to bother to compute this. I will see because this coefficient matrix is invertible. So this system is definitely consistent. So they have solution K1 and K2 such that this is true. I don't know what is K1, K2. I have to compute them, but I do know we have solution. I know the solutions. Okay, I know they have a solution. By doing a little bit more computation, I know exactly what are the solutions, but I don't need to find the solutions. I just need to tell you that this system has a solution. This system has a solution for whatever AB that you have. Therefore, you do have the span. So what is the difference between these two methods? These methods here, I'm being lazy. I'm just saying that, hey, compute it yourself. You will see what's the K1, K2, but I know system exists. The solution exists. Solution exists because this coefficient matrix is invertible, right? The solution exists. Solution exists. Whatever AB you give me, I can find K1 and K2 such that this equations hold. So what is K1, K2? I don't know. I don't care. I don't need to care. So this is another solution. I don't need to care. I just need to tell you solution exists. This is one way. This one right here, do a little bit more work because you do have the row reduce. This one actually give you more information. It says that, all right, solution exists, and I know exactly what are the solutions. Okay, but I don't need it in that much detail because if you just want to show that the span is R2, I just need to show the solution exists. This one is not only showing that a solution exists, but actually tell you what are the solutions. This one, you can say that, hey, coefficient matrix here is invertible, so solution exists, and we do have the span of these two vectors equals to R2. Okay, so this is two different ways you can solve these questions. Okay, so again, this is about reachability. All right, so right now, okay, we have a question for you. So you should try to think about how to solve these two problems. So you have these two vectors that's in R3, and the questions for you is to show that the span of these two vectors cannot be R3, which means that there are some vectors that is in R3 that cannot be written as a linear combination of these two vectors. So you cannot reach, not every vector in R3 is reachable by these two vectors. There are some of the stuff that is not reachable. When people say, like, she's way out of your league, which means this, right? You can't get to it. You can't get to it by just doing the linear combination. That's a very bad analogy, but you know what I'm saying. So there are something that is not reachable, okay? All right, so they are not reachable, and you need to show that. Okay, so let's look at this particular problem. I'm going to give you a moment to work on these problems. Then I will come back and we can look at the solution together. All right, welcome back. So what do you need to do is same as before. You take an element, arbitrary fixed element that's in R3, and you will try to find K1 and K2 such that you have this. Okay, so remember A, B, C here, they are not variables, okay? They are fixed number. You just don't know what are those numbers, but they are fixed number. These are not numbers that are going to change. This, however, of the variable. So we want to find the k1 and k2 such that k1 of this plus k2 of this equal to that. So you put it as an augmented matrix, okay? Put it as an augmented matrix. And again, because you have A, B, and C, so you can't really use your calculator to do row reduction. So you have to do row reduction by hand. It's not very difficult to do the row reduction by hand. And if you do the row reductions, you don't even have to turn it into REF matrix. Bear in mind that this is not REF matrix, because if this is a REF matrix, this thing here has to be 0. But we don't have to do it into REF matrix. Just by doing all the way to here, you will see that this system right here only is consistent if this part right here is 0. If this part right here is not 0, then the system is inconsistent. So this actually tells you, okay, what is the relationship between A, B, and C, so that it will be in the span of these two vectors. So this A, B, and C here cannot be any numbers. A, B, and C here cannot be any numbers. A, B, and C here has to satisfy some kind of relationship so that this equality will hold. So this equality will hold only when your A, B, C have some kind of relationship. What kind of relationship your A, B, and C has to have in order to have this equality hold? Well, your A, B, and C has to have this relationship. So immediately, because of that, you know that not everything in R3 is reachable by these two vectors. So immediately you can say that the span of these two vectors here, 1, 2, and 1, and also 1, 0, and 2, this is not going to be entire R3, because only those A, B, and C that satisfy this relationship will be in the span. And in fact, once you know this, you can give example. You can give example vectors that can be spanned by the vectors that's in R3 that can be spanned by these two vectors. So you can play with this 1, 2, and 1. So so you can see that you can pick up those vectors. Okay, so for example, this one right here, so you can pick elements. So this element here, you can obviously see that if you put A equals to 0, B equal to 0, C equal to 1, this will not be true, right? So this will be false. So you will know that this vector here cannot be an element that is in this set. So you can argue by example, because you actually have a lot of information here. You know that only those vectors that satisfy this form will be in the span. So obviously this vector 0, 0, 1 does not satisfy this relationship. So you can say that, hey, look, this one right here cannot be in the span. Why? Because this one right here reduces to this. So this is an easier way to do it. Is kind of like, once you see this, you can pick an element and say, hey, 0, 0, 1, if you try, you see there's no solution for that. So you cannot write 0, 0, 1 as a linear combination of these two vectors. So therefore, the span of that two vectors cannot be R3, because there's something that's missing here. There's something that's in here, but it's not reachable by these two vectors. So there's many ways to make the argument, but the key thing is nothing really new. You start from the definitions. You really start from the definitions and looking for K1, K2. That's it. There's nothing really fancy, just looking for your K1, K2, okay? So everything follow the definitions, nothing very fancy here, okay? All right, so let's look at example where we are no longer in Rn. So let's look at, say, we are in vector space P2. We can do exactly the same thing. We can ask the same thing here. So we have a vector V1. We can call this vector V1. This is a polynomial now of degree at most 2. This is a vector V2. Okay, so you have another vectors V3. So the question is, if you pick an element that is in P2, the question is this element in the span of these three vectors? Okay, so what you need to do, follow the definitions. Okay, which means that you need to find this number K1 of this V1, K2 of this V2, K3 of this V3, and see whether or not you can get 1 plus x squared. So we have seen something like this before. So we want to find the number K1, K2, and K3, so that K1 of this, K2 of this, and K3 of this will give you this. So nothing really new. All right, so now you compare coefficients. So you look at all the constant terms, okay, that give you these first equations. You look at all the coefficient for the x. You look at all the coefficient for the x to get this equation. You look at the coefficient for the x squared, you get this equation. This is the reason why we're doing this, is because in order for the two polynomial to be equal to each other, all their coefficient have to matches. So this gives us these three equations. So even though we start with a polynomial, but at the end, the computation does not involve polynomial at all, because k1, k2, k3, these are all real numbers. So you get back to the system of equations involving only real number. There's no polynomial whatsoever right here, okay? No polynomial whatsoever. So again, you know how to solve this. Put this into the augmented matrix, and row reduces to the RREF matrix. And again, because of this, okay, you will know that K1, K2, and K3, you can't find them. The system here is inconsistent, right? There's no way you can find K1, K2, and K3 such that K1 of this polynomial, K2 of this polynomial, or K3 of this polynomial equal to this. All right, so you will see that this particular polynomial here is not in the span of these three vectors right here. Okay, vectors, polynomial, same thing because of vector space. Okay, all right. So as you can see, the definitions apply equally well to all the vectors in the vector spaces, not only Rn. All right, so that's how you see that, and you can verify that this vectors 3 plus 3x plus 6x squared is one of this, and 0 of this. So this, okay, will be an element that is in the span. So some of it is in the span, some of it is not. So we know that the span of these three vectors here cannot be P2. Some of them are missing, so it cannot be P2. All right, this concludes our discussions on the concept of linear combination and span. The next concept we want to talk about is the concept of linear independence. So we're going to use that to communicate the concept of redundancy. That is, maybe we don't really need the three vectors in order to span the entire vector space V. Maybe we only need two vectors to do that. How do we be able to identify how many optimum vectors do we need to actually span a space? Do we have any type of redundancy? So that kind of questions will be answered by looking at the concept of linear independence or linear dependence. So we're going to talk about this concept in the next video. So we'll see you there.